Convolution property. Suppose x tilde and y tilde n are sequences with periodic sequences with period n, and x tilde and x tilde k form a DFS pair, and y tilde and y tilde k is another pair. Now suppose we take the product of x tilde k and y tilde k. We get p tilde k. What is the corresponding time domain sequence? Of course, the time domain sequence would be a periodic sequence with period n. How is it related to x tilde n and y tilde n? Let's recall the result of DTFT. If we have xn, the Fourier transform is x e j omega, and yn, the Fourier transform is y e j omega. If we have the product in the frequency domain, x e j omega, y e j omega, in the time domain, it's the convolution of the two. Now if we state this in DFT domain, that means we have a sequence of xn, the DFT xk, and sequence yn, the DFT is yk. Now we take the product of the two, pk equal to xk, yk. What will be the sequence pn? How is sequence pn related to xn and yn? Pn be a convolution of x and y. But then, if Pn is the convolution of x and y, then something is a little bit strange here. Why? Because xn is a sequence of length n, and yn is a sequence of length n as well. If we have the convolution of the two, like here, what is the length of this sequence? Xn has length n, yn has length n. Then what's the length of this sequence? The length of the sequence will be 2n minus 1, right? So this is 2n minus 1. And this pk is a sequence of length n. And when we perform the IDFT to get Pn, this would be a sequence of length n as well. So the length is not 2n minus 1. So this Pn is not the convolution of xn and yn. So what is it? Let's apply IDFT and find out. Let's apply inverse IDFT on p tilde k and see what p tilde n is. This is the place we should put p tilde k, right? And we know p tilde k is the product x and y, x tilde k and y tilde k. To relate it to the time domain sequence, let's replace y tilde k by y m is the endpoint DFT of y. M goes from 0 to n minus 1, and we still have w minus kn from the previous equation. So we have two summation, and we can interchange the order of these two summation. So first we can have the summation of m and y tilde m, and the other summation is k summation. We have x tilde k, and we can combine the two w terms together. We have w minus n minus m and then k. What does this look like? Does it look like DFT? This expression here, it looks like DFT, right? But with the slight modification that this is n minus m. So this is x tilde n minus m. This is IDFT, and we also need this term here together. We get this IDFT. Now we can write it as m from 0 to m minus 1, y tilde m, and then x tilde m minus m. What does this look like? Does it look like expression of convolution? Does it look like an expression of convolution? But this is convolution in a different way because the summation here only goes from 0 to n minus 1. And this is a different kind of a convolution. This is what we call endpoint circular convolution. Pn is what we call endpoint circular convolution of xn and yn. We use the notation Pn equal to xn circular convolution n endpoint circular convolution. We use this notation to indicate that Pn is the result of a circular convolution, endpoint circular convolution of xn and yn. For example, suppose xn is a sequence of 3 samples, 1, 1 and a half, 1, 1 and a half, at 0, 1, 2, and yn is a sequence of 2 samples, both of value 1. Now suppose we would like to compute Pn, that is circular convolution of xn and yn, 3-point circular convolution. So we form the periodic extension x tilde n by repeating xn every 3 samples. And we also form the periodic extension of y by repeating y every 3 samples. So 1, 0, 0, 1, 2, 3, like so. And remember p tilde n is equal to x m y n minus m sum over 1 period. In this case, n is equal to 3, so 0 to 2. And tilde, tilde. So we need xm. So let me copy xm down here. This is xm. Now we need to compute p tilde 0, 1, 2. P tilde is periodic with the period 3, right? So we need to compute 3 points for p tilde. Suppose we want to compute p0, then it's x tilde m, y tilde minus m. We need y tilde minus m. So here's y tilde minus m. I have flipped y tilde n to obtain y tilde minus m. And to compute p tilde 0, we multiply these 3 samples together, samples by sample multiplication, and then add them up, we get p0. So what is p0 in this case? p0 in this case would be, here we have 1, and then a half here, so 1.5. Now suppose we want to compute p tilde 1, then we need xm tilde m and y tilde 1 minus m. So we shift y minus m by 1 and we get y tilde 1 minus m. Here's y tilde 1 minus m. And again, we multiply point by point here, and we get p tilde 1 equal to 2. Similarly, let's compute p tilde 2. Then we have x tilde m and y tilde 2 minus m from 0 to 2. So we need x tilde m, here's x tilde m, we have to copy it here. And y tilde 2 minus m, we can shift y 1 minus m tilde by 1, and then we get y tilde 2 minus m. And then we multiply these three samples and these three samples together and sum it up, then we get 3 over 2. Okay, now we are ready to plot y. We are ready to plot the p tilde. P0 is 3 over 2, P1 is 2, P2 is 3 over 2 again, and then 3, this is one period, let's plot another period, and then maybe another period here. This is P tilde n. And Pn has only one period of P tilde. So here we go. 0, 1, 2, 3 over 2 here, 3 over 2, and 2. So here we go. Pn is the 3-point circular convolution of x and y. Now let's consider another example of circular convolution. Xn is a sequence of 2 samples, and Yn is also a sequence of 2 samples. Xn has 1.5, and both samples of y are equal to 1. And we would like to compute the 3-point circular convolution of xn and yn as in previous example. So first we form the periodic extension of xn. We repeat every 3 samples, and this is the sequence that we get, a periodic sequence with a period 3. So the samples are 1.5 and 0, 1.5 and 0, and continue on like this. For y, we have a 1, 1, 0, 1, 1, 0, 1, 1, 0, a periodic sequence of a period 3. Now we do circular convolution. Pn tilde is given in this form, as in previous example as well. P tilde n will be a periodic sequence with a period 3, so we need to compute P tilde 0, P tilde 1, and P tilde 2, and then we have the whole sequence. Now let's start with the P tilde 0. For P tilde 0, we need x tilde m and y tilde minus m. So I have a copy down x m here with a sequence like this, and y tilde m. We flip yn to get y tilde minus m, and then this is 0, 0, 1, and then 2. So if we multiply these 3 points together, then we would get, what do we have here? This is a 0, 0, so these two will get a 0. These two multiply together, we get a 0. And here, these 2 points multiplied together, we also get a 0. Only the first samples we get a 1. So this is a 1. Now let's try to see what P tilde 1 is. By definition, we would have xm tilde and y tilde 1 minus m. M goes from 0 to 2. Alright, and then what I'm going to do is to plot x tilde m and y tilde 1 minus m and multiply them together and add them together. Okay, we are going to ask a question about how this example is different from the previous one. Now we have x tilde m here and y tilde 1 minus m here, and then we multiply them together. We get 1.5. This is 1.5. Similarly, let's compute the P tilde 2. P tilde 2 will be xm tilde and y tilde 2 minus m. So we have shifted y minus m tilde by 2 to get the y tilde 2 minus m, and here's the result. And if we want to get p tilde 2, we multiply these two together, these two together, and these two together, and add them up, we get the result. And the result is only these two samples overlap, right? So we get a half. What's your answer to the question? Are they the same? Indeed, they are the same. If we perform linear convolution of x and y, and the result will be the same as this w here, the linear convolution result is the same as circular convolution result. Why? Because in this particular example, x has two samples, y has two samples, and the result of linear convolution has three samples. And when we do circular convolution, we also choose 3. Because we choose 3, there will be zeros filled in when we do periodic extension. There's a 0 filled in here and 0 filled in here. And because of these zeros, the result of a circular convolution is the same as linear convolution. Now let's state the result more generally of a linear convolution using circular convolution. Suppose x is a sequence that has length m, and h is a sequence of length l, and y is the linear convolution of the two. Then the length of y will be m plus l minus 1. Well, we will leave this as an exercise, that the length of y is indeed m plus l minus 1. Now let's call the length of y to be n. N is m plus l minus 1. Now let's do n point DFT for x, and that's xk, k from 0 to n minus 1. And for h, we also do n point DFT, we get hk. Now we take the product of the two, h and x multiplied together. We have a sequence that has length n. Now, if we apply inverse DFT on this sequence h, x product, do we get y in the time domain? Yes, indeed, this is true. And you can verify this by drawing pictures of a convolution and convolve h and k, and see that when the number of circular convolution n is equal to m plus l, then the result is indeed the same as linear convolution. Let me ask a question. Suppose you have already verified that indeed this is true. Let's say, suppose we choose n that's not equal to m plus l minus 1. Let's say we choose a number of DFT point to be, or the number of circular convolution point n to be larger than m plus l minus 1. Do we still get the same result as linear convolution? So if we choose n greater than m plus l minus 1, m is the length of x, l is the length of h, is the linear convolution result the same as circular convolution result? So indeed, we can do linear convolution using circular convolution. But why bother? Why do we want to perform linear convolution this way? This seems to be a roundabout way rather than a straightforward approach. Why do we want to go in a big circle and come back to linear convolution? The reason is complexity. So let's first examine what is the complexity that is involved in doing circular convolution this way, doing linear convolution or circular convolution this way. And if we want to do it this way, using the approach that we have done here, first we need to do, given an endpoint sequence, we need to do endpoint DFT, and we also need to do endpoint DFT here, and then we need to multiply them together. We need to multiply x and h together, and then we need to do endpoint IDFT here. So the complexity that is involved will be 2 DFT, one for x, one for h, one for inverse DFT here, inverse DFT here. So let me add that to one IDFT, and then there's also multiplication here, x and h multiply together, so we need in multiplication, MUL. So this is the convolution that's involved if we use DFT and IDFT to compute the convolution. And it turns out that there are fast algorithms for computing DFT and IDFT. So DFT and IDFT, they are fast algorithms for doing so. So the overall complexity will be smaller than doing linear convolution directly. There are a few properties that we would like to cover. Suppose x and y, they are sequences of length n, and we apply periodic extension to obtain sequences x tilde and y tilde. These will be periodic sequences of period n. And as before, we find the discussion of property on DFT more convenient if we work with the periodic extension versions, x tilde and y tilde. A little bit similar to the convolution property is the multiplication property. Suppose we have x of n, x tilde of n, that correspond to x tilde k, and y tilde n that correspond to y tilde k. Now suppose we multiply y and the x together in the time domain, then correspondingly w tilde k is equal to the convolution of x and y tilde L from 0 to n minus 1. And there's a 1 over n scalar here. We also have many properties that follow directly from property of DTFT, because after all, DFT are samples of DTFT. For example, if we do conjugation in the time domain, then correspondingly in frequency domain, we have x tilde and the minus k, or y minus n will correspond to y minus k. Question. Suppose now we do conjugation and we do flipping, time flipping, there's a minus n here. Then what is the corresponding sequence in the frequency domain? Then we combine these two properties, the above two properties together, right? Then we get x and the k tilde conjugate. When y tilde is real, then y tilde n conjugate is the same as y tilde n, right? And in this case, it can be shown that y tilde k is the same as y tilde k conjugate minus k. And this result follows directly from the symmetry of DTFT for real sequence. Very similar to DTFT, we have possible relation. Suppose y is a sequence of length n. We apply endpoint DFT on y, we get yk possible relation says that the energy of a y in the time domain, the sum of absolute value square is the energy. The energy in the time domain is the same as energy in the frequency domain normalized by n. The proof is also quite similar. Let's say we have a W sequence that is the convolution of a y tilde and x tilde. And what is x? X of n is y minus n conjugate. Y tilde minus n conjugate. Then we can verify that the value of a W at n equal to 0 is actually the energy of y in the time domain. We will leave this as an exercise. On the other hand, we also know that WK tilde is actually the product of yk, and the xk. But then using the property, the conjugation property that we derived earlier, we can show that this is actually yk magnitude square. So there are a couple of places that we will leave as an exercise. This is one step, and this is also another step that needs verification. On the other hand, we also know W sequence at time equal to 0 can be obtained from W tilde k, W, let me not use W here, let me put E, J, 2 pi over n, and the Kn, where n equal to 0, and we sum over 0 to Kn minus 1, and then there's a scalar 1 over n. When n is equal to 0, this term becomes 1. So in the end, we have Wk sum over 0 to n minus 1, and W tilde k we already know is equal to yk magnitude square. So this becomes this expression. Now let's combine this expression and this expression here and this one together. Then we get the desired result of the possible relation.